Namaskar, I am Dan Gaude, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the ordinary differential equation. First topic is initial value problem for second order differential equations. Uh, L of y is equal to 0 and second order differential equation y double dash plus a1y dash plus a2y is equal to 0, where a1 a2 are constants. Theorem first, let a1 a2 be constant and consider the equation L of y is equal to y double dash plus a1y dash plus a2y is equal to 0 if r1 r2 are distinct roots of the characteristic polynomial p of r is equal to r square plus a1r plus a2. Then the functions phi1 of x is equal to e raised to r1x and phi2 of x is equal to e raised to r2x are solution of L of y is equal to 0. If r1 is repeated roots of the equation of the characteristic polynomial p of r, then the function phi1 of x is equal to e raised to r1 of x and phi2 of x is equal to x into e raised to r1 of x are solutions of L of y is equal to 0. Prove here. Now see here, let phi of x is equal to e raised to rx be solutions of L of y is equal to 0. Therefore, L of e raised to rx is equal to e raised to rx second derivative plus a1 e raised to rx first derivative plus a2 e raised to rx, and it gives e raised to rx second derivative is r square e raised to rx, e raised to rx first derivative is r into e raised to rx and e raised to rx same as. Therefore, r square e raised to rx plus a1r e raised to rx plus a2 e raised to rx, and common them r square plus a1r plus a2 e raised to rx. Therefore, L of e raised to rx is equal to 0 implies that p of r is equal to r square plus a1r plus a2 is equal to 0. If r1 and r2 are distinct roots of p of r, then L of e raised to r1x is equal to L of e raised to r1x r2x is equal to 0, and phi1 of x is equal to e raised to r1x and phi2 of x is equal to e raised to r2x are solutions of L of y is equal to 0. If r1 is repeated roots of p of r, then p of r is equal to r minus r1 bracket square and p dash of r is equal to 2 into r minus r1. L of e raised to rx is equal to p of r e raised to rx for all r and s x. Dou by dou r of L of e raised to rx is equal to dou by dou r of p of r e raised to rx. Now, at r is equal to r1, we get p of r1 is equal to p dash of r1 is equal to 0. Therefore, L of x into e raised to r1x is equal to 0, and showing that x into e raised to r1x is a solution of L of y is equal to 0. Thus, if r1 is a repeated roots of the characteristic polynomial p of r, then phi1 of x is equal to e raised to r1x and phi2 of x is equal to x into e raised to r1x are solutions of L of y is equal to 0. Next theorem, if phi1 and phi2 are two solutions of L of y is equal to 0, then C1 phi1 plus C2 phi2 is also solutions of L of y is equal to 0, where C1 and C2 are any two arbitrary constants. Now see here proof. Let phi1 and phi2 be two solutions of L of y is equal to 0. That is, L of phi1 is equal to phi1 double dash plus a1 phi1 dash plus a2 phi1 is equal to 0. And L of phi2 is equal to phi2 double dash plus a1 phi2 dash plus a2 phi2 is equal to 0. Suppose C1 and C2 are any two constants, then the functions phi defined by phi is equal to C1 phi1 plus C2 phi2 is also solutions of L of y is equal to 0. Therefore, L of phi is equal to a1 a phi1 plus C2 phi2 double dash plus a1 into a phi1 plus a2 phi2 dash plus a2 a phi1 plus c2 phi2 is equal to c1 phi1 double dash plus a1 phi1 dash plus a2 phi1 plus c2 a phi2 double dash plus a1 phi2 dash plus a2 phi2 is equal to c1 L of phi1 plus c2 L of phi2 is equal to 0. The functions phi which is 0 for all r x is also solutions of called the trivial solutions of L of y is equal to 0. The result of our two theorems allows us to solve all homogeneous linear equations, second order differential equations with a constant coefficient. Definition, one more definition. An initial value problem L of y is equal to 0 is a problem of finding a solution phi satisfying phi of x naught is equal to alpha naught and phi dash of x naught is equal to beta naught, where x naught is some real number and alpha naught or beta naught are given constant. Now see here existence theorem statement. For any real x naught constants alpha beta, there exists a solution phi of the initial value problem L of y is equal to y double dash plus a1 y dash plus a2 y is equal to 0, y of x naught is equal to alpha, y dash of x naught is equal to beta. First theorem, there exist two solutions phi1 and phi2 that satisfy L of phi1 is equal to L of phi2 is equal to 0. From the theorem, second, we know that C1 phi1 plus C2 phi2 is a solution of L of y is equal to 0. We show that there are unique constants C1 and C2 so that phi is equal to C1 phi1 plus C2 phi2 satisfies phi of x naught is equal to alpha and phi dash of x naught is equal to beta. Now phi of x naught is equal to C1 phi1 of x naught plus C2 phi2 of x naught is equal to alpha. Phi dash of x naught is equal to C1 phi1 dash of x naught plus C2 by 2 dash of x naught is equal to beta. Above system of equations will have unique solutions C1, C2 if the determinant delta pi 1 of x naught, pi 2 of x naught in row wise, pi 1 dash of x naught, pi 2 dash of x naught is equal to not 0. By theorem first, pi 1 of x e raised to r1x and pi 2 of x e raised to r2x are two solutions of L of y is equal to 0 for r is not equal to r1, and delta is equal to r2 minus r1 e raised to r1 plus r2 x naught is not equal to 0. By theorem first, pi 1 of x is equal to e raised to r1x, pi 2 of x is equal to x into e raised to r1x are solutions of L of y is equal to 0, and delta is equal to e raised to r1x, e raised to r1x plus x naught r naught x naught r1 e raised to r1 x naught minus is not equal to 0. Thus, the determinant condition is satisfied in both the cases. Therefore, this is required proof. काय करू